start this before I totally forget. But yeah, how's it going? I hope everyone's doing well. Yeah, it's Thursday, so hopefully you guys are enjoying the wrapping up the end of the week, all that stuff. Yeah, so hope everyone's doing well since I last saw you all. Um, yeah, welcome to the last class. This is the last class in kind of the four-part seminar series on statistics and data science. So yeah, hope you guys are doing well. I gotta get rid of that waiting room, but yeah, it's good to see you guys as you guys are slowly joining. Yeah, so let's see, we've got some interesting things to cover today, so hopefully you guys are excited about that. It's a bit different from the kind of stuff that I've been slowly introducing you guys to. But like the concepts are basically, they're kind of the same. So I'll run those through with you. Once again, it's sort of really an introduction to getting you guys familiar with these tools. So yeah, really it's just kind of about exposing you guys into what we could do with these tools and really what we could do with statistics, what we could do with applications of data science. So once again, as always, don't feel pressured if you don't know, if you aren't super comfortable, if you aren't 100% an expert on this by the end of the course. There's always more things you can do with this, and there's always more ways it can get super complicated. So yeah, at the end of the day, it's really just an introduction. So hopefully you guys get an understanding of what you could be doing with data. So yeah, it's pretty exciting class. There's some really wild things you can be doing with the tools today. So yeah, hopefully you guys get a kick out of that stuff. So yeah, in the interest of time, people are still joining, but I'm gonna I'm gonna kind of start so we can thoroughly cover everything. Yeah, so welcome to day 4, last class. Hope you guys have been enjoying it so far. Yeah, so we've covered throughout the whole course, basically, covered some basics in statistics, basics in visualization, getting that hypothesis testing down, which is really a foundation of how you're going to be conducting research projects or really exploring data in the future if you do kind of continue to pursue this stuff. Yeah, really trying to aim to draw conclusions using your tools to understand your data. So today, last class, we're going to wrap up with a bit of a bang. We're going to finish with some linear regressions, kind of like correlation stuff, and also a brief little introduction to machine learning and kind of an application of what you can do with that stuff. So hopefully you guys are interested in that. I know it's a big buzzword. We'll get there as we go, but yeah, hopefully you guys get a kick out of that. So yeah, let's kind of start off. Let's start off. So first of all, I'm going to cover a bit about regression, kind of correlation, that stuff, before we get into the big guns. So this is just really also something good to know. And also it does have some relationship to the machine learning at then because machine learning really, for those of you who I guess are here for that, it's really kind of based off the statistic stuff in the first place. So it's good to have this foundation first. So yeah, let's just kind of start off, quick refresher from kind of the beginning. So this is a bit of a throwback to the first class, but if you remember, bivariate data, we never mentioned this as an actual vocab word, but you guys are probably familiar with what it actually is. It's just a data set with two variables. So like, on a scatter plot, it's what you're graphing. It's the X and the Y. Those two are the two variables. And the scatter plot can display that kind of information on the single graph. So each point represents, one data point, and that data point has those two variables, and that's where it falls onto the graph. So it's kind of intuitive for you guys, I'm pretty sure. But yeah, it can be used to basically examine whether this data has any pattern to it. So does it have kind of a linear observation, or is it non-linear? And I'll show you kind of what that graph looks like in a second. But really just lets you get a better understanding of, hey, does this data, is this look interesting? Can you see past just kind of the numbers that are given you on the table, and can you kind of like visualize that in a better plot? That's really the whole point of the scatter plot. And that's kind of why we covered it in the first one, because it's really useful to have, especially for numerical variables, because that is it's kind of hard to understand what you're seeing just with like a bunch of numbers on the table. So yeah, so your scatter plot, it's used to kind of determine this bivariate data. So when you're graphing your scatter plot, the x-axis, for those of you, in math, you're pretty familiar with this. The x-axis, that's your explanatory variable, so it's your independent variable, however else you can call it, but usually that is kind of the variable that you're using, and then x usually affects y, that whole slope thing. So then the x might explain changes in the response variable, or the dependent variable. So that variable is kind of dependent on the x variable. So you guys are probably already familiar with this with math, but otherwise it's pretty intuitive, and I'm pretty sure you guys are aware of this stuff. But when you have those kind of patterns in the graph itself, sometimes there will be, maybe it'll look like a line, or maybe it'll look like a curve. You know, that might intuitively to you, that might look visually pretty interesting. Like, there might be some kind of relationship between, like, say, height and weight. Maybe those two have some kind of relationship, and the graph is really like linearly, it's linearly adjusted. But throughout the whole course, we've really been pushing, hey, how can you not only just rely on the visuals and rely on what your gut makes you think about it, but how can you quantitatively determine this? So where's your evidence to really back this up? So, where is the quantitative proof? That is the basis of statistics, basis of data science, and really why we're pushing these tools. Because everything here, this entire course even, it's all about getting you quantitative evidence, so you can draw your conclusions, safely, and like really having that background for you. So for you, you've got to be able to judge, hey, is this linear relationship? It looks linear, but how related are these variables to each other in the first place? So mathematically, if you remember from our hypothesis testing, for us, we were like, hey, the kind of quantitative measurement, the mathematical measurement to determine, hey, can we reject the null hypothesis? How much are these two variables different? That is judged through the p-value. So in this case, our mathematical measurement is the idea of the Pearson's correlation coefficient. So um, this measurement, yeah, kind of similar as a notion, is that it helps you determine quantitatively whether this thing is valid or not. But the correlation coefficient is represented by R, and it is essentially a measure of it's a measure of the strength. It's a measure of the direction of the linear association. So, how much is it really linearly associated? And, how much is there kind of a correlation between these two variables? How much are they related? And if you do have a pretty strong correlation between these kinds of variables, what that basically really suggests for you is that there is a linear association that exists between these variables quantitatively. So you can really get that evidence. And then it kind of suggests, hey, the pattern of points, maybe if it's falling kind of in a straight line, if it's going like, negative or positive, that kind of stuff has basis to it. And then you guys are kind of free to really determine that these two variables might be correlated to each other. I do want to do want to imply this, though. This is very important and very large part of most statistics courses. The idea that correlation cannot imply causation. It does not always imply causation. So, an example is from before. If you have a scatter plot, your x variable is like weight, and your y variable is height. It's totally plausible that, like, hey, the taller you are, maybe the heavier you are, because you've got more, you've got more body mass, you've got more like space that you're taking up. So yeah, it makes sense. Maybe for everyone, the people who are generally taller, maybe they're just generally more heavy than people who are short, because, like, babies probably don't weigh as much as like a 6-foot dude. So that's kind of intuitive to us, but this doesn't necessarily mean that the heavy you are, you've got to be taller. That's not necessarily the truth here. It's just that they happen to be associated with each other. So these two variables happen to be correlated with each other, maybe if the correlation coefficient works correctly. Those two variables might be correlated, but they're not necessarily causing each other. They could cause each other. That could be a thing that you could explore later through some tests or something. Um, maybe temperature does cause, for example, like crickets to chirp more, something like that. But this isn't necessarily always the case, so you can't draw that kind of conclusion. This is a pretty like reiterated phrase throughout statistics. So yeah, usually your teachers will not be very happy with you if you ever imply that it could cause causation. So it's a pretty big thing that's drilled into your head throughout most of throughout most of these kinds of issues. So you've got to be careful with that whenever you're really looking at correlation. But yeah, yeah, if you kind of look at these graphs, yeah, these are really what I've been talking about throughout the whole time. But hey, this would really be a scatter plot. And then in this specific graph, what you're kind of saying is, hey, these lines, this is the explanatory, this is the response variable. Um, these lines seem like these dots seem to have a pattern. It seems to be really going up. What this kind of implies is, hey, the more that the explanatory variable is increasing, the more that your response variable is increasing on sort of a general basis as a general trend. And so then here, your Pearson correlation coefficient, what you're kind of saying, since it's positive, you're kind of implying that it's a positive sort of association. Um, so that there's kind of like a strong linear thing here. But then, um, if it's sort of negative, if it's sort of a downward trend, then essentially what you're looking at is that your explanatory variable, as it increases, your response variable might be decreasing. So, there's a lot of things that could count for this, like maybe yeah, there's a lot of examples. Maybe the higher the temperature, the less, you know, seeds or something sprout or something. Maybe like you're over baking them, some kind of thing like that. Um, or like, greater the predator population, the smaller the prey population, that kind of stuff. So, you know, that sort of trend, it's a negative trend. And then your Pearson correlation coefficient, you can see that it's negative. Um, that implies that it's sort of the negative association when you're looking at the correlation. But both of these really are excluding some kind of strong linear, strong linear association. But here, if you can kind of point out the correlation, it could also be at zero. So for this particular case that we're looking at here, we're saying that, wow, there doesn't really seem to be a big trend going on. Um, there isn't necessarily that much of a strong line or strong association. It seems to be pretty uniform, pretty random here. So yeah, that gets you sort of a coefficient of zero. So your the thing is that your correlation being at zero doesn't necessarily mean, as I wrote here, it doesn't necessarily mean that you have no like thing period. Like maybe if you look at the data, if you look at the pattern, maybe you have some kind of like quadratic thing, maybe you have some kind of like curve or exponential thing. um but what it's essentially trying to point out is that it is a strong nonlinear relationship. So you're really just looking at the fact that you're really just looking at the fact that, is it a linear and is it linear and is it kind of like related to each other? So that kind of thing is what you're driving home here. Um, there's different tests, I think, in the future, if you wanted to explore that more. There's different tests for you to specifically look at, hey, does this kind of fit a exponential? Does it fit a quadratic? Because there's always a lot of other data points, I think, that really fit logistic regression better, or like the kind of, logistic curve or exponential curve. If you ever work in biology, or if you ever work maybe in finance, there's like patterns in the market, or there's patterns in predator prey populations that are really not necessarily reinforced by the linear sort of association, even though that's probably always that's always a nice association to have, but it's not necessarily the only one. So keep in mind that that is also a possible thing. But for this specific scenario, when you're looking at Pearson's, not necessarily the best. It just kind of makes you understand that it's not linear. You might want to try something else. Yeah, linear regression, for understanding this basically, is really just getting this sort of line thing at its very simple basis. What it really is just trying to model this relationship between the explanatory variable and the response variable. So yeah, for this case, it is, yes, fitting a linear equation to this observed data. You're trying to find, hey, what is the equation for this line? I can model this data and yeah, really get that confirmation here. So linear regression line follows, it's pretty intuitive. I think it sounds complicated and you hear people throw it around a lot. It's pretty intuitive because it is really just finding a line. So I think anyone who's taken algebra, anyone who's gotten that stuff down, this is pretty intuitive for you. If you remember how to make a line, it's like algebraically, the equation for the form of a line period is, hey, y equals a constant plus bx, y equals mx plus b, you know, all those kind of variations, where x is the explanatory variable and y is the response variable or the dependent variable, however you call that. So it's really there's a lot of like crude ways you can do it. I know people at the very basis, like when they first start out, what people are sometimes do, they just kind of take 2 points that make sense and then find their slope between it. There's obviously better ways to do that, but really at its basis, it is trying to find out the rough sort of trend line that's going around here. So that is linear regression. And it's called linear regression because you are finding it linearly. There are different, yeah, as I mentioned before, logistic regression, that stuff isn't really modeling it linearly, you're modeling it as a different curve. But so yeah, it's different ways that you could find out really how to model that variable relationship. And so on the whole, it's pretty powerful if you are looking at trying to, if you really have these separate data points and you're trying to establish that relationship, it's very powerful in that sense for you to kind of understand that stuff. So I don't want to get into this right now because these videos respectively take like 30 minutes and I have other stuff to cover today, unfortunately. So yeah, for those of you who are interested in learning a bit more about linear regression, I will have these in the collab folder as well, I believe. But if you guys are ever interested in this stuff, yeah, feel free to click on it, do some research on yourself. There's other regression things that are also really interesting as well. So it's yeah, it's good for you to kind of get some more experience in it, find out more about it than what I told you, because this is really just a rough overview about regression. It can get very complicated, it can get very simple, but at its very basis, to me, it's really just trying to model these variables and all that stuff. And yeah, I do want to reiterate, actually, we'll get into this more when we get into machine learning, but modeling as a whole is really powerful in statistics. I don't know if a lot of people realize this because a lot of people are so focused on, hey, let's do these hypothesis tests, let's do these visualizations to try and understand, like, hey, this is, you know, whether the test works or whether the p-value fits. And that is an important part of statistics, but modeling is a very powerful tool that not a lot of people really embrace. Like, you know, the idea of mathematical modeling, it's not actually that big for a lot of people who are concentrated on that stuff. But modeling is powerful because you can get a lot out of it, whether you're, you know, you can describe that relationship and then you can really be able to derive a lot more conclusions from it, you know, rather than just kind of having to rely on hypothesis testing to kind of draw this broad overview. You get a real mathematical sort of basis for you to really derive these conclusions, maybe predict stuff, maybe, you know, classify stuff, all that stuff. So it's really interesting, and I'll get more into that when we get to what I'm talking about for machine learning. But it's really incredible. I think I'm a big proponent of you guys checking it out more if you ever have free time for that. But yeah, so let's get into real fast the collab stuff. You guys have been with me for 4 classes, so I'm assuming you guys have the drive folder up already. I'll throw it in the chat anyway, because, you know, who wants to click on that again? But yeah, once again, all the stuff for today should be uploaded in this yeah, it should be uploaded in this folder. I'll direct you to which things, because there's just a bunch of stuff happening right now. But what we're trying to focus on is this regression and machine learning collab notebook. So open that up real fast. Should take you to here, hopefully. This gets you started on some basic regression, just basic modeling here. So, all right, just a real overview, really fast. So once again, this is what the equation looks like. Loss equation, not necessarily the focus of this class. I put it on here just if you kind of want to be aware of what it is. Really, it's kind of like, minimizing that kind of error, minimizing the residual issues and all that stuff. You don't have to worry about that for now. If you are interested in it, you can try to, look that up. But just part of linear regression. It's one of the things that some people use for their models. Not my biggest concern because we're not going super in depth right now. But yeah, regression. What's I found out, because I've been poking around here a bit, the sklearn module is actually really nice, because I've been big proponent of packages throughout Python. I know you guys have been watching me fooling around with NumPy and MATLAB and all that stuff throughout this thing. But sklearn actually is really good for this sort of modeling stuff. They have these really nice models for you, including the linear regression module. So yeah, you guys don't have to necessarily remember it. You guys can really just look up, hey, how do I do a linear regression in Python? And it'll probably lead you to either the model from sklearn or some other thing someone else built. But for this lesson, yeah, we're going to be using sklearn because I like it. I like it a lot. It's really easy to use. But yeah, as always, import your packages, import your libraries, because I want to graph some things for you guys. And so for the data set we're going to be using for linear regression, I put in here, I have a postage.csv file. So down here, if you guys are following along, it's this file here, postage.csv. Make sure to download that for your reference. What it basically looks like, what the data set basically is a nice little quantitative thing. Just 2 columns, just very simple compared to everything else we've done. It's just, hey, this is the year, and this is the amount of mail postage that's being sent out in this year. Is this accurate? I'm not sure, and you probably can't draw real conclusions for it, but it's a good sort of test data set for your linear regression experience. So what we're trying to determine here, really, with this data set, once you guys got that downloaded, is, hey, is there a correlation between the number of mail postage and the year that is going on? So yeah, download that real fast and then upload it into here. So if you guys remember how to do that stuff, you need to real fast pop into your postage.csv, download that stuff. All right, so hopefully you guys are following along if you aren't too. But yeah, once you guys that downloaded df.shape, it is 57 rows, 2 columns. Good reference for you guys. Since we read in Seaborn, which is, by the way, the visualization package, if you guys forgot, it's been a while since we talked about visualization, so no pressure to force yourself to remember this. But yeah, you've got your kind of plot here. You can plot this out really nicely. And so just kind of as a basic thing, yeah, SNS, the plot here kind of gives you, first of all, the scatter plot of all the data points, and also gives you a nice little trend line for you to look at. So just visually, without doing that quantitative stuff I was talking to you guys about, yeah, just visually, seems pretty nice. It's just a nice little trend line here. It seems to fit the data pretty nicely just from a visualization standpoint. There doesn't seem to be any really severe outliers. And yeah, the data set itself is kind of tailored to this, but really it's it fits the data well. It seems like this could be the kind of data that you'd want to use to try linear regression on. So, let's try to get a quantitative standpoint on this stuff. So here we're going to use the ordinary least squares regression model to fit the model kind of test how significant this regression is. So once again, that word significant, basically, you know, how quantitatively sound, how correlated are these guys? Well, let's try it out. So OLS is pretty widely used. You should definitely look into it as you can. I won't get into that too much here, but yeah, ordinary least squares is a name you're going to see around a lot, and it's kind of the model that we're using at the moment. But here, load your module. So load your package here is statsmodels.api. You can import that stuff. And so what this can help you do, basically, you can take your explanatory variable, which is your, you know, it's your year, and then take your response variable, so your mail postage, as you can kind of see on that scatter plot. And then this is kind of important, and I will show you why in a moment, but this add constant part, if you remember kind of in basic, you know, in the thing that I showed you before, if you guys remember, this is the slope, sort of, right? You guys remember y equals mx plus b. M is the slope, but then b over here is your constant. So, you know, usually in lines, you need a constant here. This is kind of just what I'm talking about. You need to add a constant to the thing. You need to add where it kind of falls in the y-intercept. That is important, and I will be telling you why in a moment, even though it doesn't really look like you necessarily need it. But yeah, you have to have that piece of code here for this specific model. But yeah, once you can do that, you can basically fit that to your OS and then basically summarize that model that you've made. So basically, once you do this, you've just essentially you've just done a regression, basically. So pretty simple, as again, you didn't have to derive, you know, anything. It's all automated, it's all computational. And once again, yeah, that's the reason why I like Python. That's the reason why we're doing this. But yeah, you can do that real fast and you will get all these, all these crazy things. So let's talk about this. Let's look at this a bit more. If you can, yeah, if you can look at this, what you get is, first of all, the r squared is an extra thing. You can look at that more. But what we're kind of interested here is, hey, this is the, in a sense, this is kind of your p-value in a sense, but it's really your, yeah, it is your p-value here. And you know, why is there a p-value in a regression when I didn't talk about this at all in the slides? And what the p-value is really, when I mentioned before, we're testing the significance of this regression, right? So what this p-value does here, it is very small, by the way, if you haven't noticed, but the p-value basically looks at how sound the model is. So how, you know, how much does the model itself work? So the significance here, you know, it's small, so looks like the model is pretty good. You know, the model is doing pretty well for itself. And then here you can kind of more specifically look at our exact calculations, the exact model that we are looking at. So here, the year, first of all, that is the slope. If you remember, that is kind of, we depended on that for the explanatory variable. So that's in the mx plus b, that is the x in the mx. And so here they're actually able to give you the coefficient. This in your line would be your m. So that's your slope that they have calculated for you in Python. So you didn't have to derive that. That was already calculated for you. That's modeled for you. The constant, if you remember, that we just kind of threw in here, they give you this as well. So this is your b. So in your y equals mx plus b, that is your b. It's negative, so that is something we're going to come back to. But without this constant, the model itself wouldn't work. So you need to have the constant in there because, first of all, that's the definition for your line. And you know, they won't be able to function correctly without adding in this constant and making sure that they can establish where that y-intercept is. So here it happens to be negative 1729, which is a lot, but we will come back to this. And here, once again, interesting thing, this is actually the p-value as well. what you're looking at here, instead of like the p-value for the model, you're looking at the p-value for like kind of the individual, this is the individual variable that you're using. This is a type of regression. As you kind of notice, this is the kind of type of regression that we're doing where we only have one explanatory variable. So there's only one explanatory variable in the whole thing. We're directly mapping this to your response variable. That's the only association that we are letting happen right now. And because it's the only one right now, that's basically the entire model. So if this p-value were to be a bit more expanded, you'll kind of see that this and this value is actually the same. Because it's the only explanatory variable, it's the only thing being modeled to the response. That's why the p-value is going to be the same. But they ran out of lines because this is like 10 to the negative 59. So yeah, it looks like it's 0, but there is something there. It's just the same as the model. There are other regressions. There are other regressions where you are looking at, there is a probability, there's multiple explanatory variables that you're trying to map, all those kinds of things. That stuff we're not going to cover, but if that were the case, it's most likely the p-values throughout them would be kind of split up, and then, it'd be different from this. But for now, you kind of just understand that these p-values are the same here. So yeah, that's really what you kind of want to focus on here when you get this whole spit out results, is really looking at the model itself and then seeing whether it looks pretty sound or not. So yeah, if you get these results, what you can kind of say, you can plug in these numbers into your equation, and then you could say, hey, the model from this trend line, basically what the trend line is here, the model for that, the equation is, the amount of mail postage that you get, that's going to be equal to negative 170, 1,729 point whatever, plus your slope 0.8820 times whatever year it is. So that is kind of the model you can use to sort of predict, hey, if I give you a random year, what is the mail postage for that year? Most likely, what's an estimate of that mail postage that we can map out with this data and get this kind of stuff. So that's kind of powerful if you consider it. But we have to keep in mind this equation only works when the year, this is the range that I'm talking about, when the years between 1960 to 2018. So first of all, you can't give me a year in the 18,000s, and you can't give me a year in the 3000s. And the reason for this, mainly, how to determine the range in the first place is really kind of due to this constant, because you're not going to have negative postage in a sense. That's not really going to be a thing, but this is kind of what the data has limited to us to have. We don't really have data outside of that era, and so this is kind of what the data has given us based on the fact that we only have data from, I believe, 1960 to 2080, if I am correct. Yeah, it's like roughly around this point. So the model kind of gives you a bit more sway here, but really they kind of give you kind of a chop here because you can't really dip into your negative mail postage. And so with that sense, you could argue, hey, if it's negative, why not just make the year super large? why can't we have a year in the 3000s or a year in 2050 or something like that? And this limitation, this hard bar here, is really determined by, it's kind of just a statistics thing. It's statistics adequate, but the issues that come with extrapolation. So it's the issues that come with, hey, you have this model here right now, and it kind of ends at 2018. What if the data points end here, but what if we kept going? So what if we started predicting things outside of the data range? And so this is a dangerous thing to do. Usually this is something, even though it's tempting, you're like, hey, I want to predict the thing for tomorrow. I want to predict the thing for 10 years from now. It's very tempting with this, but it's not something that you can easily do without taking into account a lot of different things. There are extrapolation models, I believe, but for the purposes of this thing, it's not the smartest move, because you straight up, it's not good for you, because it's, your first of all, your data points don't extend to this, and your model is only taking into account the sort of range between your data points. So in the here and now, in the stuff that you've provided me, this is the model that I've created. This is the trend line. It's completely possible that, hey, 50 years from now, maybe there's like a maybe there's like a mail postage crash. Maybe everything collapses, or maybe everything goes even faster because, Gmail exists or something like that. But you know, something happens there, you cannot accurately map that stuff extrapolating, and it's very dangerous to do so because you don't have the data to support it like 50 years from now. So all in all, it's just kind of bad etiquette to extrapolate and just essentially go outside of the given data ranges that you have. So usually the rule of thumb, just kind of stick to your ranges. So you can predict, within here, you can try to predict, hey, what's the closest 1990? Let's see, let's check out which one. But yeah, it's not good for you to usually extrapolate here. You can also do, if you really wanted to, sklearn is, yeah, sklearn, as I mentioned before, very nice package. They use the linear regression model to do it. And I did mention this is pretty this is pretty easy. OLS is also easy if you want, but sklearn's pretty painless. But they also have a model here. What you basically do, you just take the values for the data frame, data frame year, explanatory variable, mail postage, response variable, and then you're able to fit your linear regression thing into these, into the columns, and basically print that out into, hey, what is the coefficient, which is the slope, and what is the intercept, which is the constant or the intercept. Those are the same numbers, painless, quick and easy. Plug that into your equation. You get the same thing. That is the thing within the year here. So if you want here, you can prediction per se. It's not like predicting in the future, but you can still kind of, hey, if I have this year, what will I get? I believe the reason we like sklearn, I think, a bit more is because it allows you to pretty painlessly start predicting stuff right away. You can just do linreg .predict with the current model that you're using, because you establish that your model is linreg. You take that model, if you click do the predict thing, and you say, hey, let's plug in 1980 within the year. So that year is between this range. We're in the clear. We're not extrapolating. But if we print that out, what we end up getting is, hey, this is the predicted mail postage based on the trend line that we were just using. So yeah, pretty cool, pretty pretty valuable stuff. And it seems kind of tame here because who really cares about mail postage? But you could do a lot with this stuff. You could fit data. There's always historic Wall Street data. There's historic biology data, all that kind of stuff. You can really do decent amount with predicting and being able to model this period of time. It's pretty interesting as a concept in general. So yeah, I hope you guys are if you guys are really interested in this stuff. And as I mentioned, there's different ways to do this too. Just because I showed you guys some linear stuff, I'm pretty sure sklearn has like logistic things and like showing curves and all that stuff. It's always very interesting and very helpful to be aware of the fact that you can create generally just mathematical models. So like this nice equation, it's nice to know that, hey, you can plug in something, you can totally get some kind of predicted value that the trend line is made based on data that backs it up from before. So it's interesting. I think you guys should check it out more, on your own time. But we're nearing 3:40, so I'm gonna really fast kind of switch gears because you're all here for this. And also I don't necessarily want to take up too much of your time with this stuff. So yeah, that's a quick overview in linear regression, how you can different methods and how you can interpret that stuff on Python. So there's a lot of ways to do it, a lot of people that coded it, and yeah, hope you guys dig into it more. The resources, once again, are up here. So if you want to check that out, do some more digging on your own, always encourage that. And I'm always here if you have any questions on this. But yeah, let's keep going into our fun stuff. So real fast, let's do an introduction to machine learning. So I'm pretty sure you guys have all heard about what machine learning is. It's a very popular buzzword now. It's hitting the market. People are really getting into it. But what is it? What what is machine learning in the first place? Not a lot of people understand really what we're trying to do with machine learning. Like, hey, it's AI or is it, deep learning? What's going on here? So let's jump into it. Let's see what happens. So machine learning at its very essence, at least from a data science standpoint, is really just a method of data analysis. So you guys remember the hypothesis test, you guys remember, all that stuff. This is just another tool for your data analysis. But kind of the machine learning part of it comes from the idea that you can automate it. So you as a human are not necessarily, having to forcefully identify these patterns, having to forcefully do these tests, but rather it automates it so that the model or the machine itself creates its own model by hand. So it's really just branch of artificial intelligence with the idea that these systems can learn from your data. So you apply this data, these systems learn, understand patterns, make their decisions without having a human to have to sort through it by themselves. So it's very helpful because it really gives you a perspective that you weren't really aware of in the first place. And I'll show you really what this means. But at the heart of it, this is really machine learning. It is just a method of data analysis without the human intervention. Um, it's very, very beautiful. So we will get into this more as I kind of explained. But really, it is the idea of putting in data in your computer, with some code, with some coaxing. We'll look at that data and be able to kind of create its own patterns, create its own decisions based on this data. So yeah, let's take a further look at this. The machine learning framework, I will have to elaborate on this further because you guys have not been given any examples to work off of. But this is kind of just a broad overview of really how most machine learning algorithms work off of. And yeah, real fast, I'll kind of explain this as a general overview. But what you really get here, if you remember, machine learning really is just about, giving your algorithm, giving your model, whatever, giving it data to process and understand. So that is the training data in this specific flowchart. You put in some training data, train it within the algorithm. So usually there's a piece of code for that, or there's some kind of thing that you're working with. And on just kind of a theoretical basis, what should happen is that your machine learning algorithm should take a look at that data, run on it, process it more, and then kind of end up at this trained algorithm aspect. So this is, the model that after running through all this training data has identified a pattern, identified some decisions, created some pathways based on the trends and the patterns found in the training data. And so what you can do with this is that, hey, now maybe you're given, say, some kind of testing data set. So you want to check whether this trained machine learning algorithm, whether that makes sense for you, whether the outputs, the results from these training data, whether that's applicable to other data sets of the same vein. So whether it can predict correctly or classify correctly, any kind of thing like that. What you can do is that you put that in there, it'll try processing this, and it will output with some kind of prediction or whatever outcome that you were trying to do using the trends that it understood from that training data. So at its very basis, you can kind of think of it as kind of like how the human brain works on a very basic level, on a very automated level. It's really for us, we start out as a kid, we don't know anything, right? We don't understand anything. Maybe throughout life, maybe throughout school, you will be handed, hey, this is chunks of information, this is stuff you will understand. So say, for example, you're learning math for the first time. Throughout, maybe a couple months or so, you'll be working through training data per se, or you'll be working through, hey, here's a ton of problem sets, here's a ton of things, here's how it works. all that stuff. And then you reach a point in your life where you do understand this algebra, you do understand this math, where that once you're given new data, you're able to correctly create an answer. Um, and the beauty of this here is that machine learning really kind of just does that with, hey, I had past experiences with this, so I'm going to be able to apply this to my new experiences. But instead of, a teacher having to specifically say to you, the addition sign means the two numbers go together. What machine learning does is that, hey, you'll just have a whole worksheet of like 1 + 1 is 2, and then like 5 + 5 is, it'll have a whole bunch of data that's like this. But instead of, a teacher or a human having to tell the machine, specifically addition is always, adding the things together, the machine can kind of just see all this data and seeing the patterns that come from it derive by itself. Hey, it looks like whenever the symbols involved, these two numbers add together. I'm gonna remember this, so that when I'm given my test data, I can apply this to my own stuff. So that's really the basis of it, on just a theoretical level. And so once you understand that, I think once you understand that machine learning is kind of really just, hey, you have data, you're feeding it to an algorithm or a model, something like that. And then that algorithm model understands trends in the data, and then it's able to put those trends to use into new data. That is really the whole basis of machine learning, I think, on a very simple level. That is just kind of its basic kind of theory that you are trying to understand. So that really, I guess for many, that might take away the mysticism of data, of, machine learning in general. But really, that is the core of what you try to do with these things. So it's a whole nother ballpark. Technically, there's many ways you can have your algorithm, how to recognize the patterns, how to code it so that it, understands that. There's so many technical parts in there, if you were to kind of go deeper into this. But, you don't necessarily have to understand like the linear algebra that goes into how some kind of model works. And usually what's provided to you, especially as a beginner, is you're usually just provided, the package, as we were talking about, the package or a line of code, some kind of pre-made model that can already identify this stuff for you, and you can run your data on it to kind of try it out. So yeah, we will be talking about one of these tools actually in the first place, just to give you guys a quick start on this stuff. But yeah, really, what machine learning is about here in data science, the whole point of it for us is taking data, analyzing it for us in a sense, and then being able to apply this analysis, those patterns that it's created, to other data that we are feeding it. That is the whole point. It's like automated data analysis. It's an automated data scientist. It's very helpful in a lot of different ways. So yeah, it is. I'll come back to this about what really training data means and how, trained algorithm means or anything like that. I'll be coming back to this stuff. So, and all these slides, by the way, will be back. So you can kind of look over this again if you need to. But at its heart, that is really what you're trying to do here. So yeah, let's kind of take a deeper look into this. Let's kind of check that out more. Here is, I guess, a beginning into one of the tools that we're trying to do. But before I can get you started onto the tool that I'd like you guys to check out, let's start out with a very, very basic example. So this is a very small component of the tool that we're trying to use. And let's check it out real fast. So decision trees. Decision trees are, they're a thing. So they are part of the tool that we are trying to make use of. And at its very basis, detached from kind of the machine learning element to everything, I'm pretty sure you guys might have encountered this stuff too, but really throwing everything out the window, forget about this whole complicated network, this whole framework that we were talking about. Let's just talk about this specific little structure that we are going to be closely working with. So if you understand this structure, you're going to be able to kind of understand a lot more of the stuff that I'm rambling about you. So decision trees is kind of a way that you can be sorting, parsing data, that sort of stuff. And forgetting about the automated sort of the technical aspect, I'm going to be approaching this theoretically because this is way easier to understand on a theoretical basis. But let's say for some reason you have a data set here. You have a bunch of ones, bunch of zeros. Let's say for some reason, let's just say you want to classify these. You want to sort these into little groups of, things. So maybe you want a group with only red underlined ones. You want a group with, only zeros. And you want a group with, blue zeros. So yeah, imagine our data set. This is the data set that we are working with in the first place. And so, if you want to classify it from a human sort of standpoint, you can, I guess, very visually, you can already immediately sort it. But, how are you sorting this stuff? And what you really tend to do, even if you don't really realize it, is something like a decision tree. I think you guys are already sort of familiar with that. But you make a split-second decision, but it kind of goes along the reasoning here. And the way that, the algorithm or really you'd be able to approach it is, hey, if you have a data set here, you want to sort it into different groups. First of all, if you have a giant data set, what is the thing that helps you to sort it out really fast, very easily? So I guess biggest distinguisher here, maybe it's color. Maybe you want to sort it by color first. Let's just get rid of all those zeros real fast here. Those seem to be the most different from everyone. Try to split it off. Is your thing red? Is this red? Yeah, it is. Throw it in here. Is this red? Yeah, it is. Throw it in here. Is this red? No, it's not. Throw it in the other pile. If you keep doing that, it's on a very slow basis, what you'll get is, hey, here's a pile of red things from your data set. Here's a pile of blue things from your data set. Pretty cool. Pretty easy to understand here. This data set, hey, still looks kind of mixed. Let's keep throwing some stuff. So, maybe you could say, hey, is this a 1 or is this a 0? Or you could say, hey, for this example specifically, is it underlined? Let's split the data set more. What's the clearest distinguisher? I guess everything that's underlined is kind of different from the things that are not underlined. Is it underlined? It's underlined. Throw it in yes. Is this underlined? No, it's not. Throw it in no. So this is a very small data set, but for now, even with this line of reasoning, you can see, hey, we've successfully sorted it into, here's a pile that looks like, blue zeros. Here's a pile that looks like red zeros. Here's a pile that looks like underlined red ones. Those are splitting the groups into observations. And then these groups are basically as different as possible. That's what we wanted to do in the first place. So this is very simplistic, but once you understand this reasoning, this is actually sort of what the decision trees in machine learning, in these sort of algorithms, how they work in general. So really, if you think about it, it's kind of just, you have a data set, they're trying to sort it out into kind of tiny pieces. That is a component. It's very important for these decision trees in machine learning. So, why are we having these decision trees? What's the point of these decision trees, especially in machine learning? You can use these for classification in the first place. So what we were just talking about here, let's say you wanted some kind of model that was like, I want this model, given this data set, I want it to tell me whether, whether it's a blue zero. If you use this kind of thing, then it can pretty easily sort it. It's like, hey, it's 0, it's 1, it's whatever. And, also as a side note, first time that I was grasping this in the first place, it kind of didn't make sense to me, because I think what you're all wondering is like, hey, how can a computer sense that it's red? How can a computer sense that it's underlined? There's no way that this is actually the way that it's being approached in the data. And you'd be right in a sense. The computer itself can't visually look at the fact that it's red, the fact that it's underlined, the fact that it's blue. The computer would never do this. It wouldn't kind of create this stuff. But first of all, this is kind of just a theory way for you to understand. But second of all, the computer still creates these questions, not necessarily through a visual standpoint, but maybe it'll be able to identify patterns, maybe through a quantitative standpoint, or maybe through some other thing because it's an algorithm and because it's a computer, it's able to identify these patterns more, that allows it in itself to generate questions. So it might not be, is it red, but maybe it's a different sort of outlook on, maybe there's data attached to whether it is red or not. Maybe they will use that as an identifying way to check, or maybe there's, some kind of ASCII code associated with the underlining. Maybe they specifically target that stuff when they're looking at splitting it during machine learning, but it's kind of that sort of pattern. The decision trees here, what ends up happening is that you can use it for classification. So, hey, is it red, whatever. You can also use it for prediction, as I mentioned before, kind of like, with prediction in regression models, but also, for example, hey, you could probably predict, hey, what is tomorrow's temperature here? What is temperature? Let's try doing that. And it's sort of, I think I'd like to elaborate more on this when we actually get to the code, but yeah, you can use it for classification. You can use it for predicting, hey, what's tomorrow's weather? What is it, weather given these conditions, all that things. And really all that stuff. But that's really the basis of what a decision tree is. That's basically what you are looking for when you're talking about that stuff. Yeah. So decision trees in itself, though, if you look at this might just be, it's a model generated thing. So what happens to create these decision trees on a general basis is, hey, you take your data set, so maybe like a bunch of old temperature data, so maybe like your historical data, your historical average, whatever. Take that data, put it in the model by itself generates a decision tree, and then you can feed in a number. It'll, let's say it's not winter and the historical average is, not greater than 60, and the temperature today is greater than 55, it's not greater than 55, then, it'll predict, hey, it's 52. It's 52. That might be a prediction for today's temperature or tomorrow's temperature. Yeah, that's how do you know if that's true or not? And so the short answer is that you don't know if that's true, because the thing is that this is really just one decision tree, and it is prone to a lot of errors. So maybe something in your training data set, maybe it grabbed like a very biased sample of the data set, or maybe it grabbed wrong points, or it wanted to focus on the wrong things. So the issue here is that, hey, decision trees by themselves, not a good way to classify, not a good way to predict, because it is a one-off chance that your model randomly generated based on some really quick trends. And so it could be totally wrong, because your computer, your model itself doesn't know anything about the data. It doesn't know, it has no prior knowledge, and it doesn't know, hey, winter should be cold, and historical average is usually whatever, So it's hard to gauge, especially with only a decision tree. But the method that it's doing, which is classification and prediction, we still want to use. So how can we perfect it so that your decision tree is accurate, it's more accurate, but it still keeps into, its usage of taking in data, being able to kind of like parse it, come to its patterns and conclusions, sparse it out, classify it, without really meddling with that process. So, okay, we're gonna get into that, but also, yeah, we'll get into that in a second. So that's all. That keep that in mind. I'll be back with this. I did forget to mention this one thing, and I think I'd like to get into that right now. But you guys remember beforehand when I was talking about this flow chart, and it's kind of, first glance, kind of weird, because as I mentioned before, the basics of machine learning is just, hey, take in data, run it through, comes up with its own conclusions, its own analysis, makes predictions based on some new data that you give it. But yeah, looking at this example, how did you reach this in the first place? I told you guys already, it's from training data, but if the model itself has no prior knowledge, how did it come up with this kind of stuff? So, in the first place, as I mentioned already, the computer has no idea that, winter is supposed to be cold, or that whatever is going on. The computer isn't aware of that stuff. It's got to be able to draw patterns by itself. So how we actually do this is that before I get into really decision trees in its actual usage, um, on a general basis for any machine learning thing, not just machine decision trees, what you do to generate this stuff is that you split your data. So you usually have a giant data set. So like giant data set of maybe weather patterns or whatever, your seasonal patterns, whether it's winter, summer, all that stuff. You have a giant data set of things. You split that data so that maybe like some of the columns, some of the cells or whatever are full of the training sets, and the other half or the other bunch is based on testing sets. Let me explain that a bit further. But what you're looking at here basically is, hey, during training, as I mentioned before, you feed your model basic data sets. So some kind of data set, some kind of data, some kind of historical data, maybe some kind of thing that's relevant to the problem domain. So here in the specific example that we're talking about to generate the decision tree here, our idea is we are looking at whether whether tomorrow it's going to be what kind of temperature. The data set we might be working with here could be just, hey, what's the season? What is the historical temperature during this time of year? What is the temperature that was happening today? So we can predict it for tomorrow. But during training, what you'll end up doing is that when you have, I think I can annotate this here, but if you have maybe your giant data set and you have maybe just like a ton of days, you're like, this is each kind of individual thing that you're looking at. Like maybe day 1, day 2, day 3, whatever. And then you have your factors, which would be maybe the season. Hey, is it winter? Is it whatever? You can put that all here, check whatever. What is the historical data for today? Usually, so like on June 2 last year, what was the historical data? You can put that in here. What is the season? Whatever, stuff like that. That would be your whole data set. But what you want to do is that so your model can predict the basics for any kind of data with these factors. What you want to do is make sure that it gets a little taste of what your data is so it understands your trends first. So you can split this data actually. Maybe this half you can reserve for training and this half you can use for testing. And so this training set, this is what you'd plug into your algorithm so that the model runs, hey, let's analyze the patterns between these factors. Let's analyze, the differences between these dates, anything like that. And then what it basically does is by kind of testing itself on this, it analyzes the patterns between the target stuff and the factors so that once it is run and it is totally trained based on this data, you can run your test set to test it on its knowledge and see if the predictions and the analysis that it's drawn, whether that's actually accurate for it or not. So that's really what I mean by using the training set. It's so that the model can identify any relationships between the data and the values that we want to predict. So maybe winter and the temperature is associated. So, like we understand intuitively, more likely that it's winter, the more likely the temperatures are down there. But the model has to train itself based on a ton of old winter data to understand if this factor, if the column here says winter, it's most likely that the historic data and like the data we're trying to predict for tomorrow is going to be low. So that is what that's kind of the stuff that it helps to bolster because the machine itself is not aware of this stuff. So decision trees specifically, when you're plugging in this training set, it lets you calculate, hey, what is the best questions to ask based on this training data? What is the questions that we can ask here to create these accurate estimates? Yeah, going back to my question earlier, though, it's just one tree. So you just ran it like once and maybe it grabbed the wrong subset. Maybe it's inaccurate, something like that. How can you make your decision tree more accurate in general? That is a big question, and also the reason why we're covering this tool right now. And this is the random forest. You might have heard of random forest. I love random forest. It is my favorite thing in the whole world. It's called random forest because a forest has multiple trees. That's it. That's the definition. Random forest is a kind of machine learning tool where it consists of a large number of individual decision trees operating all together. So if this is each little decision tree, this is your whole random forest model where you've maybe generated 9 decision trees, had them individually run themselves on that training data, come to their own conclusions, predict their own things, having them all run on that stuff, making sure that kind of like the errors themselves are operating all at once. They basically are able to spit out a group majority. They're all able to come to this sort of conclusion, so that the the answer that has the most votes within. So maybe if they all, some predicted 0, maybe, but most of them predicted 1. Most likely, that random forest model, it's going to be predicting 1 because most all the decision trees, based on the different factors they were using, based on the different analyses that they were looking at, most of them ended up coming to the conclusion that it's going to be 1. So most likely that model fits the best for that data. So yeah, it's democracy at its finest. Basically, it is really, if you think about it probability wise, and if you remember law of large numbers, more likely if you're running the data set, if you're running this model on the data set over and over, and it keeps analyzing these patterns, what's end up going to happen is that by putting them all together, you're going to have all these different factors accounted for. You're going to have these different parts of it accounted for. And so most likely the correct answer and the correct trends that are most important are going to be most prevalent within each decision tree for the model. So most likely, most of these are taking into account some very key issue because it's so important. Because it's so important, it's going to be present in more decision trees. Most of them will keep that into account, create these questions, spit out this answer, and that would be more likely to be the correct answer because of the trends in the data that allow it to come to this conclusion, if that makes sense. But yeah, it's really the beauty of random forest is democracy in a sense, but it's really being able to have a large number of decision trees that are not really associated with each other. So this tree won't influence this tree's decision. They're not associated with each other, but they're operating as a committee to be more accurate, because more of them account for different features, and more of them by themselves together can really corroborate and throw out any issues or any errors that come from within each other. So kind of reminds me a bit, and I guess you could kind of think of it this way. If you're like, if you're rolling a dice, or if you're flipping a coin, as I mentioned before, or in the poll thing that I was talking to you guys with the law of large numbers, if you're polling a small population, let's just say you poll them once, that's it. Your numbers could be like, hey, 70% of the population, or 70% of the poll people said yes, and then 30 people said no. But then, hey, the larger that you go, you get a more accurate representation of the population and what they actually feel like. So a snapshot might not necessarily, it could be very variable due to chance. So this is the same reasoning here. So what you're saying is, hey, one of this is just like a snapshot, one particular path that the model chose to go with the questions. But the more of these that you try to generate, and the more that you generate, the more likely it's going to reflect what the population trends are, what the data trends actually are. More likely it's going to give you that correct conclusion. So yeah, at its heart, random forest is a classification algorithm consisting of decision trees and using bagging and feature randomness to build individual trees to create an uncorrelated forest of trees whose prediction is more accurate than any individual tree. That's basically random forest. That's why it's so beautiful. And what you really need here, I'm going to skip a bit here because it's not necessarily that important. You don't have to know necessarily about bagging and feature randomness or bootstrapping or any of that. You can look those up in the future when you want to get closer with this stuff. But at its heart, you're able to get features with predictive, you want features with predictive power, and you want to make sure that these trees don't influence each other. So let's put this into practice. I'm sure you're all eager to try this out. So once again, get into that same collab sheet that I was talking about in the drive here. And so real fast, I want you guys to download this temps.csv. It's about, once again, the question, it was like, hey, can you predict tomorrow's temperature? Download this real fast because you're going to need this in a second. But yeah, for you guys, I'm just going to keep going for now. So I mentioned before it's a classification algorithm, but I want to kind of showcase real fast because we have 20 minutes, some of the stuff you can do with this. So it is a classification algorithm at its heart. It's very helpful for this. A lot of people use it. And so I'm going to kind of show you guys how nicely it works here. So let's say you have this data set, right? This is the iris flower data set. This data set is actually very famous in machine learning. Pretty sure other wave people have used this for their other things. But it's very nice. It's a very clean data set. It has basically, I don't know too much about flowers, but what it gives you are these 4 sort of features. So you get the sepal length, sepal width, petal length, petal width, and then the type of flower corresponding to whatever those things are. So the kind of task for this issue is, hey, you're given these features, you're given your sepal length, width, petal length, width. You found a random flower in the wild. You want to identify what type of flower it is, like what kind of iris is it? So you can use random forest actually to build a model and try to classify what kind of flower you're looking at, given the fact that you know sepal length, sepal width, petal length, petal width. So you can actually do that with random forest. You can classify it based on these features. So this data real fast that's very nice. It's actually in this sklearn package. So what you can do here, import it and then load this data set. You'll get this iris data set. You can do a really quick sneak peek as to what it actually means here. You can print the different flower names. So, you know, the kind of flower type that we're looking at, and then names of the features. So it's the sepal length, width, petal length, width, just get an idea of what your data set looks like. Here's actually a quick little printout of the first few, first few rows of it. Can give you the, these are the length, width, whatever. And then, that's important to know. And then those are basically the features that you're looking at. That's the length, width, whatever. You're using these features to try to identify the target, which is basically whatever the iris, whatever flower it is, what kind of flower. The way that it's currently encoded for your machine purposes is that you're basically assigning each flower type to a key kind of a thing here. So the Setosa flower type is marked as a 0. So all these things are zeros. And then, so these are all Setosa flowers. Ones are versicolor, so these are all versicolor flowers. And all the 2s are Virginica flowers. So yeah, what you have in this data set really is this giant thing of, just giant thing of, hey, these are the flower features and what they mean. So what's the answer key, basically? So what kind of flower is it? This is ugly though, so I think we all kind of want to get an idea of what it looks like. So let's use pandas. You guys remember, that's your nice reformatting thing. You can use pandas real fast and reframe it. So here, what it looks like basically as a nice features thing. If you remember, 0 is our Setosa flower. So all these attributes are one of the Setosa flowers. Another few of these attributes, another individual Setosa flower. Keep going, lots of data, things you can do. But yeah, let's make the model. Let's start with the random forest. So remember when I was talking about training the data? We have a blank model anytime, but how can you make this model tailored to the specific experience? What you've got to do first of all is make your training and your test data sets. So um, what you've really got to do is this. You can kind of come back to this later because it's a bit it's a bit confusing, but this is a nice package that lets you train and test. It basically just splits the data set into a training and testing function. So if you remember here, this is the X. It gives you basically the features. So the length, width, whatever. This is the stuff that, on a best case scenario, you have your model, you want your model to take this stuff in, and then your label or your target is what you want your model to identify. So best case scenario at the end of the day, what we want is a working model that you can take this X data in, and then it'll input, output, the Y data. So take in length, width, petals, whatever, output, hey, this is blank type of flower. That's the best case scenario for a classification. We need to split that up so that you have these features and we have these labels here. And then once you have that split up, you can kind of move it into a training and a test data set. So here what you've got, this function that I was just talking to you about, you can put in the features, the labels, and then the size that you want your test set in. So basically the size that you will use to check whether your model has made correct predictions or not. You can check that, and then it'll give you, from this specific standpoint, it's a 70% of the original data set is being used for training the model. 30% of the original data set is being used to test the model and whether that trained sort of model is accurate. So you can run this real fast. It'll split these up into their respective sort of variables here. And then you can start training. You can start that stuff. So model we're using, sklearn, love that thing. Instead of the regression stuff, it is now random forest classifier. So you can create this classifier here just with like, hey, this is the amount of trees that you want, and then train this model here. We name the classifier CLF. So what you do here is CLF.fit, and then for the training data sets, you want to give them, first of all, I want to see, hey, these are the features, and then what are the answer keys for the features, so they can get, the model can start to train itself on, hey, this, maybe a bigger sepal length is related to the species 0, or maybe a smaller petal length is related to species 1. You want to give them all the answers here so it can start training themselves and understanding the patterns. You don't need to know the patterns for this because that's machine learning. It'll derive it for itself. What you just need to do is train it here and then basically get that stuff done. Once you trained it, basically your model is that point on point, the trained data set that I was just talking about here. So, hey, we trained this here, it's trained. Now let's test it. Let's make sure that it's accurate based on the stuff that we just ran. So here we can predict with the current trained model here. And what you end up getting is, that CLF.predict, just put in your X for your test. So you just want to try, hey, I'm going to give you the features in my test data set. I'm not going to give you my target because I don't want you to know these answers. I want you to tell me them so I can verify whether this is correct. So I'm just going to give you, and this is why we split it in the first place, I'm just going to give you the X test. So let's try this out real fast. We ran that. And then this is basically all our predictions. So we have the predictions here, but we want to check whether that's accurate or not. So we can do this really nicely with sklearn import metrics and kind of run that through real fast. So what you'll end up getting here is, hey, how often is this classifier correct? We trained it already. We tested it. How are the test results matching with the data that we have in the test results? So if you remember, the answers technically for our test test set is Y test. And so you want to match, hey, how is Y test, these actual answers, how does it match up with the Y pred? So the Y that they predicted from your X tests. You can run this and it'll give you an accuracy from this metric stuff. Hey, this looks like this model was 95% accurate. So that's pretty nice. Maybe it missed a few, based on some, maybe some data patterns were different for this test set. But for the most part, looks like the data that we trained looks pretty good for itself. So yeah, really that's really classifying, and that's really being able to run it. Now that you run your model, you have pretty much a working model. You could fine tune it more if you had time to, but 95%, that's pretty good given the fact that you have such limited data. What you have now is basically a working model. So the original goal that we had is, hey, you pick a random flower off the street, you want to classify it. You can do this now with individual features. So let's say you have that outside flower. You picked it off the street and you know that you measured it out. You have, hey, sepal length of 3, sepal height of 5, petal length of 4, and petal width of 2. Hey, I want to know what flower this is. I want to know what type of flower this is. I can go to this model. I can do the clf.predict with the trained model. Run this through, you'll get array 2. And if you remember here, we coded these into, we coded this into different species so that if you remember here, what they're saying is that this is the Virginia flower if you're talking about this stuff. So you can change up these numbers however you want, depending on whatever happens. So, Mike gives you, hey, this is a different flower now. I reduced that petal length and I reduced that sepal height. It seems to count for, the ceratosa flower. So this seems pretty complicated, maybe, but at its, like, from a coding standpoint, I hope you can kind of all agree. It's very simple. It's really just a couple lines of code, but you have to understand the process, which is, first of all, reformat the data to look good for the model or whatever model you're doing. Training it, well, first of all, splitting the data into your training and test sets, training it, testing whether the trained set is accurate, and then basically you have a model that you can use to do whatever you want with. So it's pretty cool. That's pretty nice for your classification. I did mention, though, you can do more with this than just, hey, I have a flower and I want to make sure which group it fits into. This is very useful, by the way. This whole setup for classification, whatever, this is extremely useful because, aside from just like flower classification, you can do a lot with it. Like, hey, if with this, let's say microbiome data set, you can classify if this patient is like, hey, are you type blank diabetes or are you type blank illness, or with business or something, maybe you can take this portfolio, take this kind of trend line or something like that with the data. You can say, hey, does this match blank scenario? Is this classified with blank scenario? This is very helpful if you open your mind to different ways that you can use for classification, not necessarily just like sorting things or like, hey, that is a cat, that kind of stuff that people tend to do with neural networks or anything. But very useful, very important. But yeah, you can do more than that. You can actually predict. And I did mention this in the slideshow. That like, hey, you can use it to predict tomorrow's weather, things like that. But it's important to know because it's really kind of just, in my opinion, it's a bit like using the same classification format because you're taking into account like, hey, this is, you're trying to classify it into some kind of thing. You're using the same process and you're using the same tool. And I'll show you here real fast because we only have 7 minutes and I want to get through this because this is important to me. But yeah, if you remember before you wanted to download that temp set here, make sure you download temps.csv. And then what you can do here, what you have in that temp set is kind of the example that I just covered from the slideshow, which is, hey, I want to predict the temperature for tomorrow in some city using a year of past weather data. Features basically that you're having here is the year that it is, the month that it is, the day that it is, week that it is, the temperature a few days before, the temperature, a day before, the historical temperature for the day that you're looking at, and the actual temperature that it was. And then maybe your friend's prediction if you wanted to do that too. But that's what the data set contains. So let's try this out real fast, how I really would try to construct a prediction for this thing. If you remember before, we were looking at temps.csv, so it's pretty nice. You can upload that real fast. Sadly, not as there, but what it looks like here, yeah, you've got your features. This, if you remember, is the target. Everything else kind of is a feature that we're thinking about. So keeping that in mind, this is just a process I had to kind of do because it's it has to do with like the issues that come with weak and how the how the model reads that stuff as a feature. You don't have to get too deep into this because this is really just you have to read the model. You have to understand how it intakes data. So this is it depends on a case scenario, but this is you had to do some reformatting, so run that code. Once again, if you remember here, you want to split it into the labels and you want to split it into the feature names because you're going to be using different portions of it for each training versus data set. I don't know why that's, oh yeah, I didn't run NumPy because I'm good at this. Let's see. What's that? Ooh, somewhere. Anyway, it's here. Did it quit on me? Anyway, but what you happen to do, yeah, if you remember there, you have to run the, make sure you run the data set, make sure you run the, there you go, yeah. So that splits it into the training, splits it into the test set. It's pretty nice. And then, yeah, right here, split it into training, split it into test set. Kind of exactly what we were doing in the first part. And then, yeah, start predicting. So what you can do here, you've got to basically, first of all, just as a baseline here, so we can kind of understand the impact of the actual model, let's do just a baseline test first. So this is like, hey, if our model doesn't improve on that, then basically what I'm telling you is that this model doesn't work. So this, I'm just trying to basically showcase whether this prediction works. You don't necessarily have to do this all the time. It's good to judge whether your model's working or not. But what we can say here is, hey, let's say that last year was basically a perfect measurement of the year that we are trying to predict. Now we're going to say that if we were to say the previous historical data, that is our old prediction. So error for that with the actual versus last year's data is like 5.05. Let's try to beat that. Let's make it more accurate. So if you remember the process, train our data and then test the data. Let's train it here, import the model, maybe like 1,000 decision trees, and then train the model with the, first of all, the features and the labels in the training set. So the answers and the questions, the data that they're trying to look at. They train the model, look at them go, very funky. And then let's try this, let's predict it. We have a test data set, we're just gonna give them the features from the test data set, see if we can predict from that stuff. So, hey, is this prediction gonna be more accurate? Is it not? If you run that stuff, if you do rf.predict and rf is our model, we can test it on the test features and we get these predictions for what the model thinks it is. So let's try to, if we were to get the error like they were doing here, what you get is 3.87 degrees. So yeah, what does that mean for us? If we look at our baseline, that is what happens if we didn't really look at the trends right now. We didn't look at any other features and we were just like, let's say the historical data is the same. It's 5.06 degrees. Here we've reduced it. It's like 3.87 degrees. What does that mean? That means our model, at least it's more accurate than just using last year's data, and reusing that stuff. That means that, hey, our model is able to somehow have been able to parse out which features might be more important for it, maybe, what day it is or, what kind of season it is, that stuff. It's able to parse that out and it's able to create these predictions that are a bit more accurate than the previous predictions for the training set. So yeah, we don't really have a lot of time, so I'm gonna start having to let you guys go soon. But really, this is just the rough overview of what it does. And to me, I think, personally, It's kind of a lot just like classification. They run the same way. And really, you are still the basic framework. You are still, hey, this is your data, analyze patterns. Does it fit into whatever thing that the label is saying is correct? And so this is really just the specific example here. It's kind of classification, but you're trying to put it in, first of all, in a continuous target value, and also, you know, you're able to put it in as sort of a prediction because of the idea that you had the historical data to back it up here. So it's yeah, it's really it's really interesting how you can really apply these things, whether it's, hey, I want to find out the weather for tomorrow, or hey, I want to see what kind of flower I am randomly classifying, stuff like that. But yeah, that's basically the that's basically the end of the class. I think that's a whole bunch of things. I do have to, before I totally let you guys roam free, I do need people to fill out this form. So click on that and then fill that out at some point. This is a wave thing they wanted us all to do. So hopefully you guys fill that out at some point. I'll put this in the ed thread too if you guys miss it. But yeah, it's real nice to have everyone here, and it's real nice that you guys are interested in data science and were willing to come to the class. So I'm really thankful that you guys signed up, and stayed with me throughout this, participated, and kind of was on me with this nice little journey. I hope that everyone, I know you all have different levels of beginner, different levels of whatever. Wish you success on your data science journey. And honestly, um, wherever you go, I hope this introduction helped you a bit so that you kind of got you more curious, got you more helpful. I do run a nonprofit for data science. It's called Data Horizon. So if you guys are interested in, possibly doing things with that, we work with data science. We work with that stuff. You guys can feel free to contact me at my email here. Just kind of ask about, whether you'd be interested in doing some stuff for the nonprofit or learning about more things in our seminars, something like that. Um, but yeah, I hope you guys hope you guys are interested in data science. Hope you guys enjoyed the class, and that you have a great day.